Here we are again looking at stereoisomers. It's been a little bit since we've talked about isomers, so as a refresher, a stereoisomer is a compound that has the same molecular formula, but what is different is the direction of equivalent chemical bonds. We have already talked about geometric isomers. These are going to be our cis and trans isomers. We are now going to be focusing on our optical isomers, also known as chiral carbons. What make optical isomers is the difference in placement of a substituted group. Like we had seen with our cis and trans, whether it's talking about the alkenes with their double bonds or the cycloalkanes where they cannot rotate around the ring, here the center carbon is called the chiral carbon. That chiral carbon has 4 unique groupings that cannot be overlapped. We will be investigating 2 types of optical isomers, diastereomers and enantiomers, throughout the next series of videos. In order to be an optical isomer, a carbon needs to have chirality. Therefore, a carbon can be classified as an achiral or a chiral carbon. For the most part this semester, we have looked at achiral carbons. Achiral carbons means that the carbon is bonded to 2 identical groups. If I have 2 identical groups, as I have shown or have built here in my models, so I have a yellow group on each of my structures, a purple group, and 2 red groups. It's the 2 red groups that are the same. So right now, what we're looking at is a black, yellow, purple, and 2 reds. What this means is these 2 structures can become superimposed. Superimposed means they can lay on top of each other and be identical. When this is the case, the carbon that we are investigating is considered an achiral carbon because it's able to match up. Achiral carbons will not be an optical isomer. It's chiral carbons that we really need to focus on. In a chiral carbon, the carbon we are investigating needs to have 4 different groups. And these 4 different groups cannot be superimposable, which means they cannot lay on top of each other and match up at every single point. Here we have 2 identical. There are 4 different groups. We have a yellow, purple, blue, and red group. Therefore, these carbons are chiral. No matter how I try to lay these together, I would have 2 groups that match and 2 groups that don't. Again, no matter how much I try to rotate and put and match up, I cannot get all 4 of these bonds, all 4 of these groups to match up perfectly. That's what it means to be non-superimposable. Under that category of non-superimposable, we have our 2 different types of chiral isomers. Enantiomers means there is a mirror image. So if we have a mirror here, the yellow is looking at the yellow, the blue is looking at the blue. The purple is behind and forward, and the red is behind and backwards. That is a mirror image, and that makes an enantiomer. If I were to move two groups around, because the chiral carbon cannot really be changed, it is no longer going to be a mirror image. Two atoms remain because they're really on the same plane. But if you notice, this purple that is going behind is now a red going behind. And then we have the purple and red intermixed there. No matter how I try to rearrange this, two groups will always be out of alignment. When we have that situation where there's not a mirror image, this creates a distereomer. What we can do when we're given a structure, we are going to look at each individual carbon to identify whether or not that carbon is chiral. Looking at carbon 1 first, I like to use different colors for my different groups because color really is a good association. On this first carbon that I've identified, 3 of my groups are hydrogen, and 1 group is all that other stuff. It's a very scientific term. Because it's got 3 of the same group, this carbon is not a chiral carbon. Therefore, it is achiral. On this next carbon, or carbon 2, I've got a methyl group, I've got a hydroxyl group, I've got another methyl group, and I've got a hydrogen. As you can see, I have 3 colors represented here, and we need to have 4 different colors in order to have a chiral carbon. Therefore, this carbon, number 2, cannot be chiral because 2 of the groups are methyl. And if we look at carbon 3, it's the same. It's a methyl group. 3 of the groups are hydrogens. Therefore, this is also an achiral carbon. With no chiral carbons present, this is a achiral compound. General rule of thumb is if you have a CH3 or a CH2, these 2 cannot ever be chiral. They will only ever be achiral because they will have multiple groups of hydrogen. So as you're going through a structure, if you see a CH3, you can ignore that carbon right away. If you see a CH2, you can ignore it. Then you know you only have to pay attention to the one that does not have repeat hydrogens. Once you've figured that out, we can start the process over again. Here in yellow, we have a methyl group. In green, we have a hydroxyl group. In blue, we have an ethyl group. And in purple, we have a hydrogen. As long as one of the carbons in the compound is chiral, that compound becomes chiral. Now you're probably wondering why there's a snail on the title page. Snails also have chirality, and there's chirality a lot in nature, and we'll talk more about that in lecture. But based off the spiral of the snail, it can be a right-handed snail or a left-handed snail. And right-handed snails can only mate with right-handed snails, and left-handed snails can only mate with left-handed snails. So chirality is really prevalent within our ecosystems and life, that it's showing this pattern that we are just going to be recognizing in our organic compounds. Try it on your own. Go through each of these compounds and identify for each carbon whether or not it would be an achiral carbon or chiral carbon. If there's at least one chiral carbon, it is a chiral compound. So pause the video and give this a shot. I am going to, just for those of you who need it, pop out all of the bonds represented in this first compound. We have CH3, CH2, CH2, C that has an H and an OH, C that has an H, H, H. So we have all of our carbons, popped those bonds out so that we can take the time to process every carbon. I'm going to number them 1 through 5 from left to right. So we're just going to go down that line. Again, I like to use colors. If you want to use a highlighter, you can. This time I'm going to draw squares so that I can erase them as we move down our carbon chain. On carbon 1, remember I repeat a color if it's the same group. So here I've got 3 hydrogen groups and 1 other group. I'm not going to name it because I don't want to. But it is different. But because it has 3 of the hydrogen bonds, because it has 3 of the hydrogens, that is going to be an achiral carbon. Looking at carbon 2, I have 2 hydrogens, a methyl group, or a CH3, and something else. I have 3 different groups. 2 are the same, therefore this carbon is going to be a chiral. So we do not need to worry about it. So that is again showing you that if you have a CH2 or a CH3, you can just bypass them. That means on carbon 3, if we go through this process again, it's got 2 hydrogens. You can stop right there. I repeated the same color. Because there's 2 hydrogens on there, this is an achiral carbon. I'm going to move on. Going to carbon number 4. On carbon number 4, I've got a hydrogen. I've got this propyl group, so a 3-carbon group. I've got a hydroxyl, and I've got a methyl. 4 different colors, 4 different groups. That means that this carbon is chiral. Therefore, we have a chiral compound. And we will say it has 1 chiral center. That becomes important when we talk about our monosaccharides. Looking at our next compound. This COOH is a carboxylic acid. Because it has a double bond, it can't be chiral because it only has 3 total groups, and we need 4 groups, or a tetrahedral, to have a chiral carbon. So I'm going to ignore my carboxylic acid. Going to carbon 2, I have this carboxylic acid, an amino group, something else, and a hydrogen. Carbon number 2 is considered a chiral carbon. Going to carbon number 3, we have a methyl group. We have this other group. We have a hydrogen, and we have an ethyl. Carbon number 3 would be considered chiral. I'm going to go off to the branch off carbon number 3, and because it's got 3 hydrogen on it, we know that that carbon cannot be chiral. Going down to carbon 4, it's going to not be chiral because there's 2 hydrogens, and carbon number 5 will not be chiral because it's got 3 hydrogens. Due to the presence of 2 chiral carbons, this is a chiral compound, and it's got 2 chiral centers. In summary, go to each carbon, color code your groups. You don't need to name them. If there's 4 different colors, it's chiral. If there's not, it's not.